Hello, welcome to Space Door Live, and for the first time in a long time, my audio is working perfectly, I think, as soon as we started to talk. So a very warm welcome to you on Space Door Live. Thank you for joining us. We've got a thunderous talk for you tonight. We've got on the show Professor Chris Scott. He's a professor of space and atmospheric physics at the University of Reading. And tonight, we're going to be talking about space weather. Hey, Chris, thank you so much for joining us. How are you doing?
Hey, Latch. Yeah, all right. Looking forward to this.
Yeah, me too. Well, wherever you're joining us from across the world, remember you can use the comment section in YouTube and Facebook to chat with us throughout the show. And later on, we're also going to be having a live Q&A. But before we do that, I'm going to let Chris set the scene for us. So away you go, Chris.
Right. Thanks, Lax. Well, I've got a few pictures to show you. It's 11 years since we launched Solar Stormwatch, which was really born out of having too much data to know what to do with. And I'll just run through a few of the events that happened and talk to you about how we actually came to devise the project. So I was working on a mission called Stereo. This is a NASA mission, which is two spacecraft moving out from the Earth in Earth-like orbits, looking back at the sun to try and track any eruptions from the solar atmosphere known as coronal mass ejections or solar storms. Because if one of those comes towards our Earth, it can have big impacts for our modern space technologies, such as satellites and even power grids on the ground. So understanding when these are going to erupt and when they're going to come towards Earth is very important if we're going to protect some of our modern technological assets. And the UK had built a camera on the side of the spacecraft called the Heliospheric Imager, which was a revolutionary new camera, which is going to take really wide field views of the space between the sun and the Earth. And I got to go to the launch. It was really incredible. There's a picture of me at the Kennedy Space Center with a badge saying VIP visit around it. It was hopefully it wasn't the pinnacle of my career, but it was certainly a high point. And it was a night launch, very spectacular. And the reason I was there was because of this. This is the Heliospheric Imager. It's a box about just under 1 meter long, and it has two cameras in it that look between the sun and the Earth to see if we can see anything coming. Now, the technology that goes into this instrument is astonishing because the sun is just outside the field of view of this camera or these cameras, and yet we're trying to image something which is 100 million times fainter than the sun itself. So which is the solar wind, which is the material that's constantly being blown off from the solar atmosphere. So the technology involved was amazing, and these cameras were going to really revolutionize our view of what we were going to see. And this is one of the first solar storms we saw in the mission. But just to show you what it's like, you don't actually see the sun in this image. This is where the sun would be. I'll put a little orange dot there. And this is the planet Mercury down here, and then this is the planet Venus here. And if I scroll through these images, they're about an hour apart. You can see a solar storm erupting from the sun and heading out into the solar system. And we can talk about it later, but if you really don't want to be living on Mercury because it has no atmosphere, and these solar storms blast directly into the surface of that planet. So that was one of the first storms we saw, and I went on to BBC Sky at Night with Sir Patrick Moore. It was a seminal moment for any space scientist to be able to discuss your mission. And off the camera, I got talking to Chris Lintott, who's one of the presenters on the Sky at Night, and I was basically saying, we've got all these images, and it's going to be incredibly challenging to actually extract all the information we need from all of them in a comprehensive way. Well, Chris has just set up, or had been using citizen science projects where people have been helping with his astronomical research, and he put me in contact with a group at the Royal Observatory at Greenwich. You can see the observing dome on the picture on the right there. And we put together a project called Solar Stormwatch. And in this project, we asked people to come and help us to look at our data, to identify features, and to try and get some as much science as we possibly could out of them, because we were a small team in the UK of about 4 or 5 researchers at the time. But one of the things we asked people to do was to track the CMEs through movies and tell us when they reached halfway, and then look at that in both cameras, because we have a binocular view, a stereoscopic view of these suns erupting, these storms erupting from the sun. And so if we can actually triangulate on the fronts of them, we could actually tell what direction they were moving in. So that was one of the projects we asked people to look at. And then there was odd things that happened occasionally in the frames. And this is an example of a micrometeorite strike on the spacecraft. Spacecraft are covered in what's known as multi-layer insulation. It's like a space duvet made out of lots of reflective material. But if a very small dust particle hits the spacecraft, it can knock little bits off that, and they drift through the field of view and give all these sort of big dagger-like stripes across the images. So the first thing that we were able to do scientifically with stereo was to actually map the dust that's in space at Earth's like orbit. And that was a real example of how, with people looking at the data, you can discover things that you didn't expect to discover. And so the more people looking at it, the more science you can get out of it. Now, the stereo science data was sent back once a day via the great big dishes of the Deep Space Network, but there was a much lower resolution version of the data that enabled us to do real-time tracking of these solar storms. And so we were able to look, and you can see in this sequence of images here, a solar storm erupting into space. And because it's coming in both cameras, again, we know that it's heading towards our planet. And so the volunteers were able to actually make what were called fearless forecasts, forecasts before you could be proved wrong as to what direction they were traveling in and what time we thought that they would be reaching Earth. Well, here's our first publication. As I mentioned earlier, it was looking at all these dust strikes on the spacecraft and actually mapping where the dust clouds were in the orbit around space, in Earth's orbit in space. And it was a specific size dust particle as well that we were looking at, and we could tell that from the rates at which they were hitting the spacecraft. So that was completely unexpected, and it turned out to be the first paper that came out from the project. And then my PhD student at the time, Kim Tuckerhood, had to look at these beacon mode, these low resolution information, and try to use those to track storms to Earth. Now, this is a data product. We've taken slices through each of the images and we've lined them all up. And so a feature moving out from the sun should appear as a line sloping up on these graphs. That way. No, my mirrored camera is confusing me, but it's sloping on the graph. And the figure below there shows you the data gaps. That's what we were actually trying to track them with in real time. So stereo is a science mission. It was meant to be looking at these things after the effect, but here we were trying to do something that stereo again wasn't designed to do. And we can do that with volunteers, because with volunteers around the world, we always had somebody looking at the data. We always had someone trying to predict when it was coming. And Kim was able to put all their predictions together and actually show how these data could be used for real-time forecasts. But it was not particularly effective because the data was so sparse. So then my colleague Luke Barnard worked with the data sets to actually look to see if you could automate the tracking of these, if you could have an automatic routine to identify features. But because we had all these manually identified features by the volunteers, we could use that to understand how good the automatic routine was. And that had never been tried before, actually automatically identifying these features in our images. So again, we were able to advance and test our theories by comparing it against what the storm watchers were seeing. We had several articles where we were actually tracking the fronts of these CMEs, and you can see here these red boxes represent the consensus view of where we thought the fronts of these CMEs were in the movies. And we were able to build quite a comprehensive catalogue of all these solar storms, these solar mass ejections as they erupted into space. And then my current PhD student, Shannon Jones, before she even became my PhD student, this is for her MSc project, one of the things in Solar Stormwatch was to take what we saw in our heliospheric imager cameras and map them back to the sun to see if we could see where they'd erupted from. And the result that Shannon got was really interesting because we had so many CMEs, these solar storms that we could track, we could actually show that there was a systematic deflection of the CME from where it was erupted to where it ended up in space. And so that helps us understand how these things propagate through space. And again, it's another important factor if we're to understand and forecast accurately these storms arriving at Earth. So that was the original Solar Stormwatch. We then moved on to Solar Stormwatch 2. And Solar Stormwatch 2, we were getting quite excited about what the possibilities were. And so in Solar Stormwatch 2, we actually gave the volunteers individual images of these solar storms and asked them to draw around the edge of them. Now, this is something that a computer finds very difficult to do. And so these are the sorts of projects that are absolutely ideal for human eyes. Our brains are brilliant at pattern recognition, and so we got people to draw around the edges of all these storms in every frame that we had in our movies, and we were able to actually have a very accurate, for the first time, very accurate measure of the position of the fronts of those storms as they erupted out. And you can see on the two movies at the top there where we've overlaid the consensus view of where the fronts were. And it's a subjective opinion. If you get many people to give you the subjective opinion, if everybody agrees, you know it's a very strong possibility that that's where the front of the storm is. And so again, that's really helping us to understand where the fronts are moving and when we expect these things to arrive at Earth. And then Luke Barnard again did some fantastic work looking to actually tie down every possible unknown. We got every last piece of spacecraft data so that we could track these storms. We looked at assuming that they were a simple shape. And if you assume they're if you assume they're a simple shape, then actually you don't do a very good job of forecasting. So the conclusion was that if we put all the information we can possibly know, we still don't understand, because these things are being distorted and becoming completely misshapen as they come out into space, because there is the solar wind. This is the constant outflow of material from the sun's surface, and there are jets of fast wind and slow wind. And so as this storm comes out, some of it is being accelerated by the fast wind, some of it is being held back, and so the shape is constantly evolving. And so this was very good evidence that we couldn't just assume simple shapes for these storms, and that we did indeed need to actually take into account this distortion as they propagated outwards. And most recently, we've had a very successful collaboration with the Science Museum, who are hosting an exhibit on the sun. This then left the Science Museum in London and moved around the country. And they wanted to have a citizen science project to accompany the exhibition. And so the picture on the bottom right there is Roger Highfield from the Science Museum, myself and Shannon, and Professor Lucy Green, who was one of the curators of the exhibition. And what we proposed to do was to look to see the complexity within these storms. So normally we've been looking at the fronts of the storms and how they had misshapen, but inside these storms, some of them look really complicated. Other ones just look like a balloon, of sort of a light bulb going off into space. So we asked volunteers, we gave them pairs of images and just said, which one of these looks the most complicated to you? And they were able to rank pairs, and we were able to use some statistical analysis to actually then align all these in order. So which were the least complex, which were the most complex. And Shannon did a great job doing that and got another research article out looking at that. And the interesting thing is if you arrange these mass ejections you give them some complexity ranking and then plot them as a function of time, this is what you see. So you see at the bottom of this graph there, this is the sunspot number, which is an estimate of how active the sun is. When the sun's very active and throwing lots of these storms and has a very complex atmosphere, it has many sunspots, and that goes over an 11-year cycle. And we could show that the complexity of these storms actually followed that cycle. So when you have a very complex magnetic field in the solar atmosphere, that leads to what looks like a complex magnetic structure of these clouds of hot plasma as they come into space. So that might seem an obvious result, but it wasn't one that had been tied down before. And so that's where we are at the moment. We've actually got this project which we ran with the Science Museum, which was able for us to actually start examining the complexity within these storms. So there's more. Every time we ask a question, we have more questions to answer. It's been a fantastic journey.
Wow, thank you so much for setting the scene, Chris. I guess my first question is, for people listening as well, is how is space weather different to like the weather we see here on Earth?
Well, by space weather, what we mean is the sun and the solar activity and how that affects our Earth's space environment. So with the Earth on the ground, we're used to having climate, which is the sort of long-term behavior of the atmosphere. And then within that, there are weather patterns. So over a shorter period of time, you might have a hurricane, or you might have a very cold snap, and those are the weather aspects within the climate. And it's the same with space. So there is a certain radiation environment which it has long-term changes, but we also have these storms, these solar storms that can erupt from the sun. And each one of these storms is about 1 billion tons of material erupting at 1 million miles an hour. So we're talking about a lot of energy here.
Wow.
But they are enormous. They dissipate in space quite quickly. And if you think of the Earth as a tiny little pinprick in space, then as these storms wash over the Earth, the magnetic fields that they can contain can interact with the Earth, and that enables energy to be extracted from these storms, and that's what causes the aurora. Now we do have a cartoon, I believe, of this process in place to show. So you can see with that video that the Earth has a magnetic field in space. It's a protective magnetic bubble. But these storms, because they can bring with them magnetic field, those two magnetic fields, if they're oppositely aligned, they can actually join together. And that stretches the Earth's magnetic field out into this big long tail, like stretching a bow on a bow and arrow. And then as that snaps back towards the Earth, energetic particles are accelerated into the atmosphere. And that gives us the beautiful aurora, the northern and southern lights. And if you've got energetic particles flowing in the atmosphere, that represents a current. And so if you have an electric current flowing in the atmosphere, that can induce currents to flow in the ground. And that's not good for the power grids we have on the ground. So it can just change the radiation environment for over the matter of a few days.
And you mentioned that people have across the world have actually been contributing to understanding the impact this is having on the Earth.
Yeah, so the Solar Stormwatch project has something like 20,000 volunteers, active volunteers taking part. And because they were tracking our data so and actually characterizing the shape of these clouds so well, it gives us the best possible chance we have of tracking them through our cameras and predicting when they'll be arriving at our planet. And this is a science mission, so we're doing it after the effect. We're not trying to do genuine predictions with the science data, but everything we learn how to do helps us understand how we're going to do it properly once we do have a space weather monitor. And there are plans to have a permanent spacecraft monitoring the solar wind so that we can do this.
And can people who are listening in the audience right now, and if you're watching this on catch up, how can they get involved in projects like this?
Well, Solar Stormwatch is just a website, www.solarstormwatch.com. It's one of many, a family of citizen science projects run by Chris Lintott and his group at Oxford under the auspice of Zooniverse. So that's the zooniverse.org. And if you go to the zooniverse.org pages, you can see a whole multitude of projects. So if solar storms aren't your bag, or you're feeling you'd like a change, there are all kinds of different projects, and not all of them are science-based now. So some of them are looking at ancient manuscripts. You're helping to translate ancient manuscripts, or looking at wildlife cameras to try and understand what populations of animals are seen in certain areas. So if you have an interest in trying to do something with historical data or science data, then there is a project for you at the Zooniverse.
And I guess the first question I have is, like, what type of skills do people need before they do it?
Well, I guess it does depend on the project, but
especially in terms of like the solar storm projects, do people need like previous knowledge or understanding of it, or can they just turn up?
No, and in fact, actually, I think a lot of the exciting discoveries that have come out of the citizen science projects have come from people approaching it with a completely a novice eye, because I firmly believe that there's no such thing as a stupid question, especially in science, because if people ask a question, they make you look at the data, the images in a different way. And so, for example, with the dust analysis, we didn't realize just how enthusiastic our volunteers were going to be to look at these dust strikes. And so that was one of the data sets that was completed early on. And particularly one of our volunteers, Elizabeth Barton, who characterized almost half of it by herself, and ended up with their name on the paper. So it really is useful to have people coming at it with no preconceptions whatsoever, because we're making subjective judgments about where we think the edge of this cloud is, and we're trying to project our understanding onto it. But this is so new that actually I think people characterizing where they think the edge of these clouds are is so much better done if you don't have a prejudice. And the great thing about these Stormwatch projects, the Zooniverse projects, is that you get the wisdom of the crowd. If everybody agrees what they think the answer is, then you can be fairly certain that that's a well-defined cloud. Whereas if you've got some people saying, I think the edge of the cloud's over here, and some people think the edge of the cloud's over here, and without even seeing the image, we can just think, okay, well, that's clearly not a very clear image. And so we can also then look to see which are the sharpest events and which events perhaps we need a bit more information about.
And what kind of age groups can get involved? Is it kids as well who can get involved, or is it
absolutely anybody? If you're capable of wielding a mouse and clicking on images, then yes. And people are also quite worried about getting things wrong, or accidentally clicking in the wrong place, and that really is not a problem, because the chances of everybody clicking in the wrong place is next to nothing. And so it's not like if you're doing 20 or 30 classifications a day, and you accidentally get one wrong, and you think, oh no, that my reputation is in ruins. Because we're asking lots of people to look at the same data, and it's through finding out where people agree, that's where it's the important thing. And you can spend as little or as much time on it as you'd like. You don't have to. You can come in, you can dabble, you can click a few storms, and you can think, that's not for me. Fine. If you spent 5 minutes doing stuff on our project, we're still grateful, because 1,000 people spending 5 minutes is still an awful lot of time.
Yeah, I think what I find really fascinating is that the general public is actually contributing to like these PhD research papers, and it's something that you don't generally think of. Like when you imagine PhD research, you imagine a person doing intense research for a year or two in something really, really defined. This is like thousands of people from across the globe are helping contribute to this one research paper. I find that really interesting.
Yeah, I feel really humbled that I've effectively had 20,000 research assistants, and we've been able to do things that we wouldn't otherwise have been able to do. And we do put a link into the papers saying this
Yeah.
is aided by contributions from the volunteers. And if we can link through to a page which has everybody's user IDs on too. So there is a way of accrediting a lot of people, but also we do look to see, and if one volunteer has single-handedly contributed a large amount to the project, then we often invite them to be an author on the paper too, because they have had such a profound impact on it. So I think it's wonderful that people who haven't had the opportunities to study to follow a science career, but who nevertheless are are very interested in science,
still
still
interested,
have an opportunity to contribute, and maybe undo all the years of hurt that poor careers advice they were given at school.
Yeah.
I mean, not that everybody has to be a scientist. I absolutely agree.
Exactly.
Everybody has to have a whole range of skills. But if your calling was to do something different, you can still indulge your inner space scientist by coming and helping with this project, or your inner biologist by going and looking at one of the wildlife projects too at the Zooniverse.
Exactly, yeah. Well, just a note to everyone tuning in, if you have any questions for us, let us know in the comment section below, and we'll try our best to answer them. Let's talk a bit more about the impact of space weather then. Like, what do people have to look out for? Should people be worried about if there's a solar storm coming?
Well, we as a society need to be worried about it, but individuals should take some comfort that the governments around the world are aware and are taking measures. So in the USA, under NOAA, NASA's sister organization, there is a center, the Space Weather Prediction Center, which is looking at providing a space weather forecast, if you like, so the equivalent of a weather forecast, so that people who are running technologies that are potentially vulnerable to this have some sight of what the conditions are in space and in our space environment at the moment. And in the UK, that same job is done by the UK Met Office. So the same people that provide us with our weather forecasts, there is a division there that are actually looking at operational space weather forecasts. So they do the same thing. They mirror the forecasts that are being done from the United States, and they run the same computer model. So it's a similar sort of process. With weather, you get lots of information, you run it forwards in your comprehensive computer models, and you see what you do that many different times with slightly different starting conditions, and you see what the outcomes are going to be. And it's the same with space weather. We try and look to see how we could possibly predict when these storms are arriving. But if you think about how the weather forecast was before the space age, so sometime in the 1950s, where we didn't have those glorious satellite views looking down on the planet, and you can see all the storm fronts moving across, and you can see exactly when it's going to make landfall on your country.
Yeah.
With space weather, we're sort of in that position. We haven't got a spacecraft above the solar system looking down and being able to track when all of these storms are coming. We have effectively got 2 or 3 space meteorologists in little lifeboats bobbing around in the ocean, trying to make spot measurements and look on the horizon to see if anything's coming. So we don't have that great wealth of information that Earth-based meteorologists have, but we are making the best of what we have to do good forecasts at Earth. And the reason we care is that when one of these storms come towards Earth, as I said, it brings with it hot plasma, so electrified gases from the sun's atmosphere, and with them is wrapped up the sun's magnetic field, and that interacts with our Earth's magnetic field, and so it can cause deviations of compasses. It can sort of have, so there's some sort of navigational issues there. It can cause currents to flow in the atmosphere. Those cause currents to flow in the ground. If those currents get up into the power grids, they cause surges of power that those grids weren't designed to take. And so it has been known, for example, in Quebec in 1989, there was a big solar storm that caused a power surge that actually burned out the transformers for a number of days in Quebec. So it can actually have a big effect like that. So if you're a power operator, you want to know when one of these things is coming so that you can take evasive action. And the one thing that you can do is you can just open up every wire on your network to dissipate these currents as widely as you can, so that no one circuit is carrying an excess load. And you have to worry about it if you're a spacecraft operator. You don't want to be uploading delicate software updates to your spacecraft at that time. And so if you know that it's going to be a bit choppy in space, you think, okay, well, I won't do that today. I'll do that next week.
Yeah. Well, you spoke about the impact on navigation. Is it something that maybe airlines should be more worried about?
Well, with the airlines, it's usually a communications issue. So the Earth is a slightly squashed ball, so it's actually shorter to fly over the North Pole to go to America than it is to fly around the side. So all of our commercial flights, or most of them, go up over the auroral region. And if there's a solar storm happening, there's lots of energetic particles coming into the atmosphere, and they're being stopped very high up at about 100 kilometers up in the atmosphere, maybe a little bit lower if they're very energetic. But that can change the nature of what's known as the Earth's ionosphere, and that's the electrified part of the Earth's atmosphere. And aircraft can use that to reflect their radio transmissions over the horizon. So if the ionosphere gets disturbed, then an aircraft's ability to communicate with ground control or air traffic control is compromised. And so as a consequence, they might have to reroute somewhere where the radio transmission is more reliable.
And what about like defense mechanisms that we potentially can put in place if we know that something is coming 10 years or 15 years down the line? Once we have more understanding of the weather, what can we do to help protect us?
Well, one of the things we need to do is we need to understand the extremes in the space environment. So, and if we know that, then we can generally protect the electronics in spacecraft so that they're not so badly affected. And the more shielding, the more redundancy you put into spacecraft, the bigger and heavier they get, and the more expensive they are to launch. And so there's a real sort of payoff there between making your spacecraft super reliable and making them vulnerable to the effects of space weather. So understanding the extremes of space weather is an important thing. And then once you know that, the engineers can engineer to cope with that. So there are ways that you understand what the worst case scenario is. You can do that. The biggest storm that we know of that arrived at Earth was what's known as the Carrington Storm, because it was seen by a flash of light on the sun that launched this solar storm towards Earth was seen by the astronomer Richard Carrington in the UK. And 17 hours later, there was a big storm hit the Earth. But of course, back in 1859, we didn't have satellites, we didn't have power grids to speak of, and we didn't have aircraft. And so the zenith of the technology at the day was the American telegraph system, which was a big, long wired system running down the coast of America. And currents flowed through the telegraph system. There were fires. There were people who got electric shocks. There was even one operator apparently who disconnected the batteries from his equipment, and it carried on working because there was just so much electricity flowing through.
Wow, okay.
So we can estimate how much energy came in to the Earth during that storm, because we know that the aurora came very far south, almost to the equator. Now, the aurora marks the boundary between the sort of closed magnetic field lines that are protecting our planet and those that have been opened up to space by connecting with one of these storms. And if you think of the Earth's magnetic field as like shells on an onion, as the storm passes, it can peel temporarily shells off this onion into the tail, stretch them out, and eventually they will flip back. So it's not something that is lost forever. But if you have more the field being eroded near on the sunward side, you can erode those field lines down, and so the energetic particles get in at much lower latitudes, and so the auroral ovals move down towards the equator. And for the Carrington event, they were seen at really low latitudes, so we know that there was a lot of interaction between the solar storm and the Earth. Now we don't know, but the Carrington storm could have been 2 CMEs. So to use a sporting analogy, in American football, if you had a blocker ahead of the person carrying the ball, or even in rugby, if that person is able to, if you can think of one CME stopping the solar wind and clearing the path for the second CME to come out really fast and have nothing slowing it down, there is no solar wind to slow the second one down. It can arrive at Earth without decelerating very much at all, and so it can have a much bigger impact. Now we think one of those storms happens once every 100 years or so.
Okay.
And the governments around the world are looking to set up the Met Office in the UK and SWIPC in America, and there's the an equivalent in Australia and a few of the other countries too. And if you have any kind of advanced warning, you can limit the damage, but also you can make sure that none of your critical infrastructure relies on technology that is going to be compromised by a space weather event.
Okay, wow. Okay, that's so interesting. So that means that if it's once every 100 years, does that mean we're potentially due something soon?
We certainly saw a storm that was as fast as the Carrington storm in, I think, 2012, but it didn't come towards the Earth. It actually went over one of the stereo spacecraft, and it blacked out the images in the stereo spacecraft for a couple of hours because there was just so much particle radiation in the vicinity of that spacecraft. So we know that they happen. It's just when will they come towards Earth? Now that the sun has an 11-year activity cycle, we don't know quite what the chances of having a big event are at different parts of the cycle. Some people think it might be in the sort of declining phase as it's just coming out of the energetic side. But the sun has been abnormally quiet for the last cycle or so. And so it might be that space climate is changing and we are heading into a much quieter period of solar activity. Or it might just be that the sun's building up for a big one. So we don't know. We're still looking at that. And there's lots of people looking at the sun and the solar activity cycle to try and understand what causes a big cycle and what causes a small one. But it's just it's like any catastrophe, it's an alignment of coincidences. So you'd have to have the Earth in the right place, you'd have to have the right magnetic configuration in the sun's atmosphere, and possibly you'd have to have 2 mass ejections going off one after the other so that the second storm has a path cleared for it so it can travel straight towards the Earth.
I mean, I don't want to say it, but a little bit like calm before the storm. What's happening right now?
Yeah, well, you can't win, can you? if you're worried about it being a calm space environment, but we are aware, and the governments are aware, and they are talking with people in the power industry and in the aviation industry and in the satellite industry to make sure that the risks are known, and they've all got risk management plans in place. So if anything happened that was worse than the Carrington storm, then who knows? But the Carrington storm is the baseline we're working to at the moment.
Okay, that's interesting. Well, there's a question in from the audience from the Ringler family, and they're asking, are there any new citizen science projects that you guys are considering in the near future to study the sun?
Yeah, well, there's so many things that could be studied, but one of the things that we're quite interested in doing, I'm hoping to get the space store involved when the store opens again, is to look back at historic space weather and historic sunspots, because we do have an understanding that there were auroral events in history. You can look back through ancient Chinese catalogues and they will see aurora, and obviously they may not have understood the reason for the aurora in early history, but they nevertheless give us some indication of what space weather events were like. So one of the things I want to do is to look at early sunspot observations and try and see, because there are some records of people who've seen sunspots from the ground, and they say we saw a dark spot on the sun. And of course, if the sun is considered to be a perfect celestial object and suddenly it's got acne, that could be a terrible portent of doom, and the emperor might need to know. And so when something like that was seen, we know that it must have been a certain size, but actually we don't actually know what the limit is there and how big that sunspot should be. And generally the bigger sunspots are associated with the bigger storms. So we'd like to put up have like a sunspot eye test in the space store, and actually see if we can find out if people can see what size of spots people can actually see.
Yeah, I think that's something we'd be incredibly interested in getting started, especially because we know we've got so many space fans and we're building this online space community, especially through these Thursday night talks. And I'm sure once the store opens again, we can get people down to our store in Didcot in the south of Oxfordshire and have a look at sunspots. I think that would be really interesting. An interesting question coming in from Angered Jeffrey, and he's asking, could this knowledge or technology be a threat, potentially be weaponized? I'm not sure. I think he means in terms of a solar storm coming in. Can that be weaponized? I'm not so sure.
Well, the one thing that you have to be aware of is that we have a lot of objects in space at the moment. There's a lot of space junk, a lot of satellites, and there's some military satellites there too. And you can be assured that the government are tracking all those satellites and wanting to know where they are. If you have a big space storm, then it heats the atmosphere expands out, and the drag on those satellites changes temporarily. And so there's then a frantic search to make sure you can lock and identify where all those spacecraft were again. So I think it's fair to say that there are times during these space weather events where you would be more vulnerable to some malign attack than others. But again, that's something that the governments are well aware of and are making provision for. But I think there was an example during the Californian wildfires. There was a big solar storm, and that disrupted radio communication. So it in and of itself, it may not be the thing that causes a disaster. But if you're relying on radio communications to communicate across a wide area to deal with some other disaster, then a space weather event on top of that will just make your life a whole lot more difficult.
Yeah, I mean, imagine COVID without the internet.
Yeah,
potentially.
Yeah.
Well, let's talk a little bit more about how you got involved with space weather, because I know even your PhD is in upper atmospheric physics, which sounds really interesting. So yeah, once again, let us know if you guys have any questions in the audience. But yeah, how did you get involved with space physics?
I had two interests as a child. I grew up on the south coast, and I used to go fossil hunting, and I used to do astronomy because it was fairly dark skies in the village where I grew up. And so when I went to, I always kind of knew I wanted to be a scientist. I thought perhaps I was going to be a paleontologist. I didn't know quite how to spell it, I don't think. And when I went to university, I studied both geology and space physics. And I just didn't get the way that the geology was taught at the university. And looking back on it, now I'm a university lecturer. I question how well it was taught, to be honest. I remember we would talk, and maybe it's just the way I think. I kind of want to learn. I want to have everything in some kind of logical progression. But rather than being taught geology in terms of the age of the rocks, or where the rocks were from south coast to north coast, or the types of rocks, we were just given this mishmash of information, because each lecturer had their own speciality, and they were interested in it. And then you as a student was left to try and kind of put all that together. And I can remember one of my colleagues coming into my room and saying, how are you getting on? And I was saying, well, I think I've just got another 320 million years to go. So when it came down to choosing, I think I kind of reluctantly let that go. It was a discipline that wasn't for me, and there were people within my cohort that were thriving at it. So it can't have been wholly down to the fact that it was taught badly, but I think it was taught in a way which didn't really appeal to me. So then I switched my attention to space physics entirely. As I told my geology teacher, I'm going to stop looking down and start looking up. And my degree was a very interesting one in that it was looking at physics and its applications to astronomy and space science. And so that encompassed planetary science and astronomy and cosmology, but also the Earth's atmosphere. There was quite a big atmospheric physics group there, and the Earth's upper atmosphere and the ionosphere, which is where the atmosphere kind of interfaces into space, I think is a region that kind of caught my imagination, because it was astronomy, it was planetary science, but it was local to us, really. And it was I mean, we're very privileged with our sun. It is a star, but it's so close we can study it in a lot of detail. So by understanding our sun, it gives us a much better understanding of perhaps the mechanisms that are going on in many other stars. So that's why I ended up in the discipline I am. And then my PhD was studying the aurora. It was studying how the ionosphere and the kind of neutral atmosphere interacted with each other during one of these space weather events. Because if you have electric currents flowing in the atmosphere, they're constantly bumping into into the neutral atmosphere and heating it up, and so that's what causes the neutral atmosphere to expand. So my PhD, if I look back on it, it was 3 years working out how efficiently an oxygen atom would hit into an oxygen ion or vice versa, and comparing it with the theoretical result. And the end result was the theory is pretty good, actually.
That's usually what happens at the end of science experiments at school as well. They just tell you to prove a theory that already exists, and you're like,
and that's what's nice about these citizen science projects too, is that we're not giving you a project that has been done before, many times, and you can kind of, I think the best physics teachers manage to disguise the world weariness that they must have in doing the same experiments every year, but with a different group of people. But with the research projects on the Zooniverse, they are genuine research questions. These are things that we don't know yet, and I think that is something that really does inspire people, because it's not just going through the motions, it's about actually furthering our scientific understanding.
Yeah, definitely. I think anyone who's interested in kind of getting involved with these research projects can definitely check out Zooniverse, which is run by the Oxford University, and check out Solar Stormwatch if you're interested in that. The websites are on the screen now. I'm super interested in talking a little bit more about your role as a lecturer and researcher and how that ties in with the space industry.
Goodness. Well, I think what we're trying to do, there is an operational space weather forecast, as I said, and they use techniques that they have, they use the models that they do. And I think what we're in the process of doing is to look at the latest data, develop new techniques, and see if we can improve on what is already being done. And we have very close relationships with the group at the UK Met Office, so that if anything that we were doing started to show merit on a forecasting basis, then we could start having discussions with them about taking that over into the operational side. But because the operational side has to have such reliability and such it has to be robust, then a research project where you're trying out a few things and you're thinking, well, it sort of works. That's not good enough. You have to make sure that your code is to the right standard, and that your techniques have taken into account as much as you possibly can. But bit by bit, we're able to, and not just my group at the University of Reading, but all the researchers in the UK and overseas are looking to just make tiny improvements, and hopefully great improvements on these models and on our understanding of these things. So I mentioned that there is a plan for a space weather monitoring mission, which is going to fly out to away from the Earth and then stop. Stereo never stopped; it just carried on drifting out and around, and then it's crossed over and it's coming back round again. I'm afraid one of the Stereo spacecraft, Stereo B, is no longer working. But if we were to fly a spacecraft out and stop it, we would actually have not a sky view of the weather, but we would have at least an offset view, so that we could look along that Sun-Earth line and see what's coming towards the Earth. So the things that we can understand now and the techniques that we can develop hopefully can be applied to future missions. And they also feed into the science of future missions, because if there's something which we feel we really do need to get a much better understanding of, then of course that helps feed into the questions of the next mission that's coming up.
And what can people look forward to coming up in the next 5-10 years in terms of, do you expect this to be kind of taken up by the science industry a bit more and getting people involved in looking at images and trying to answer questions that take a lot of time?
Yeah, I think with citizen science, it has taken. There are still some people that view it as just glorified outreach. It is that they view it as, you're letting people come and play with your data in a very sort of benefactory kind of way. But it's not that at all. I feel super grateful to anybody that spends time on the project, because if they do that, then they are genuinely contributing towards research. And so I think more people are starting to realize the benefits of this, particularly when you have so much data now. I mean, Stereo was launched in 2006, and it brings back hundreds of thousands of images. But we now have missions like the Solar Dynamics Observatory, which is in Earth orbit. It's making better than HD images of the sun every few seconds, I think. And it has its own dedicated ground station, and it downlinks something like 1 terabyte of data a day. And if you think about that volume of data, a small science group cannot possibly look through all that data. And so if you have a science question that you're interested in answering, then just getting people to look at the data is so super helpful, because people flag the data and say, this particular image has one of the features that you might be interested in looking at.
Yeah, I guess it's a win-win for everyone, isn't it? Like, you get your outreach because you're involving people in science and you're telling everyone more about science and getting them involved in terms of how solar weather is actually could impact us. And then you're also saving time and progressing. You're doing 5 years worth of work in a year because you've got so many more people.
Yeah, and I think it's enabling projects that we wouldn't even anticipate trying to do, because the amount of work is so enormous. I should say that on each of these projects in the Zooniverse, they have a forum where the users can talk with each other and they can show each other the pieces of information that they found interesting. And I've kind of watched with. I think that was one of the things I was most nervous about starting up the project, was that I would have to spend a lot of time on the forum explaining to people what to do and how to do it. But actually, you have to answer those questions a few times, and then they go into an FAQ, a frequently asked questions list, and people can be referred to that. And then you can get onto the second order stuff. And I remember we were looking at there had been a solar storm around the same time as an earthquake in South America. And so one of the users from South America who had been affected by that earthquake said, I always knew that solar storms caused earthquakes, which is, it's a coincidence if it's only on one occasion. And I didn't know quite how to respond to that, because I don't think that's correct. I don't think there's any evidence for that. But the other users set up their own experiment, and I watched on like a really proud dad. All these the people. Okay, well, that's our theory, right? Is that solar storms cause earthquakes. Okay, well, we can go off. We can get all the data about earthquakes, and we can plot those. So they plotted out all the earthquakes, and here are when all the solar storms happen. Plot all the solar storms, and they don't match at all.
Yeah.
So
Yeah.
on that basis, while this does look like a solar storm has caused the earthquake, if you look across a whole lot of data, that doesn't happen. And that is the storm watchers developing their own test, their own science, their own hypothesis. And I think that's something that's so wonderful, is seeing people working out what science is. It's about asking those questions and then trying to devise an experiment that will test those questions. And I think that skill, whether you work in science or not, that skill is a really important one if you want to be able to have some way of testing what somebody has told you is true or not. And I think that's very powerful, given the ability for misinformation to be propagated on the internet and through the media at the moment.
Yeah, no, I think what you guys generally are doing is extremely powerful for the science community and the space community. So hats off to everyone who's involved in these projects, and to you guys for creating this platform and setting up so that people can have an impact. Do you ever come across experts on your forums who are like, oh, maybe it should be done a different way? Or is there ever any controversy?
I think there are differences of opinion as to the techniques that we've gone down. But the thing for me with the data, and we haven't shown a lot of the movies because I've been talking too much, I think. But I think it would be nice to just show some of the other things that we've seen in these data. For example, we've got these big wide field cameras. We see so many comets, and so there are some beautiful examples of comets interacting with the solar wind. And we could look at, for example, Comet Encke, which we actually saw one of these CMEs, one of these solar storms, come out and knock the tail off the comet. That really was quite spectacular.
Oh, okay.
And that stuttered a bit for me, but in the frames, and you can go onto the NASA stereo website. If you go to nasa.gov/stereo, you can see a lot of these movies. But that tail of that comet got swept away as the storm went past it. And astronomers have seen for hundreds of years that the tails of comets get detached, and nobody quite knew why. And so when we understood about the solar wind, that became the theory. But here we were actually witnessing it happen. We could see the storm erupt. We could see it take the tail off the comet. But one of the other amazing things we've seen was with planet Mercury, and the video of this is quite stuttery because it's very zoomed in, so it can be a bit speckly. But with the planet Mercury, you can actually see a tail of material eroding off the back of the planet in the solar wind.
So if anyone ever denies solar storms exist, you can just show them that video.
Yeah, so that was the planet Mercury. I don't know how well anyone could see that, but at about 10 o'clock, there was a little tail of material, and astronomers from the ground had seen that Mercury formed a tail in space, and it's sodium. It's the old-fashioned sodium lights that glow in that yellow color. If you look at those particular wavelengths, you can see this big long tail coming off Mercury from the ground, and we were able to see it from our spacecraft too. And so there's almost no photon lost in our images. We've got all these stars in the backgrounds that the astronomers are looking at. We can track asteroids. We can look at the planets. There's so much more science to do with just these cameras, and it's not necessarily the science that we set out to do with the mission initially.
Yeah, no, that's great. I think, I presume coming up over the next few years, there'll be more and more data to analyze, won't there?
Yeah, so there's two very exciting new missions at the moment. There's Solar Orbiter, which is ultimately going to go up and over the poles of the sun to look down on part of the solar atmosphere we've not really been able to look at before. And there's the Parker Solar Probe, which is in this fantastically elliptical orbit, which is skimming it through the sun's atmosphere, so that we can see up close and personal all of the twisting, contorting fields, and we can look to see how is the solar wind accelerated into space. We still really don't know the mechanisms behind some of that. And so there's going to be, every time you launch a new spacecraft, there's a whole new swathe of data as well, and the more people that can look at it, the more we'll find.
Yeah. So would you say we're still in our infancy in terms of what we know about space weather?
Maybe not infancy, but certainly we are. It's a very young discipline in terms of scientific disciplines. I mean, we've only had the space age since the late 50s, early 60s. And as I said, a big space weather event is expected maybe once every 100 years. So we don't even have 100 years worth of space data yet. So looking back at the historical data, looking forward to these new missions is going to really help us to sort of build on that data set and understand the context of these things.
Great. Well, that's incredibly exciting. Just a note to our audience, thank you so much, everyone, for joining us. It's been a pleasure having you guys join us. It's been a pleasure speaking to you, Chris. I've learned so much more about space weather that I didn't know before. I hope you enjoyed it. Thank you for coming on the show.
Yeah, it's been great. Thanks.
If anyone has any last-minute comments or questions, let us know in the comments section. And if you guys want to learn more about Solar Stormwatch, visit the Solar Stormwatch website, solarstormwatch.com. Have a look at what all the cool projects that they're doing. Go across to Zooniverse as well. They're doing some great stuff. And I think we'll wrap up the talk there. It's been a pleasure speaking to you, Chris. Thank you to everyone who's joined us on the show. Remember, if you're new on Space Still Live, make sure you subscribe to support our growing space community. And we'll be back next Tuesday at 7:30 with our fortnightly space roundup with space experts and astronomers Nick Howes and Terry Mosley. Thank you so much. Also, if you want to visit the Space Store shop to support us, go over to the Space Store website, spacestore.co. Our store's currently closed, of course, if you're in the UK. We're still in lockdown. So our store is currently closed, but please go support us. Check out our website. And another exciting news, if you didn't join us on Tuesday, a couple of days ago, we were speaking to an astronaut. So go check out on our YouTube channel. We were speaking to former NASA astronaut and record holder Michael Lopez at Alegria. So check out that talk as well while you're there. And yeah, thank you so much for joining us. Oh, I think we have a couple of minutes to squeeze in ground-based spaces question with ground-based spaces saying, with big organizations working on somewhat controversial satellite webs, should they be encouraged to look at defense from solar storms if they're not already? And I think this is something we briefly spoke about offline in terms of the Starlinks. But what do you think about that, Chris?
Well, these Starlink satellites are small satellites in low Earth orbit, and the reason that astronomers are upset about them is that if you look into the night sky with a telescope trying to build up images of a very faint object, and the chances are that one of these low Earth orbiting Starlink satellites will drift through your field of view and spoil your observations. So that's why they're controversial. But they, with astronomers, but they are providing a global internet supposedly. But they're in a fairly low Earth orbit, as I understand it, and so they will be vulnerable if there are space weather effects that heat the atmosphere up. That will cause a drag on the atmosphere, and it will prematurely shorten the length of individual satellites if they're dragged more than was expected. And this has happened before. So the Skylab mission at the end of the Apollo era, that was in an orbit that was decaying. It was the precursor to the International Space Station, and the idea was, as I understand it, that the space shuttle would be launched and it would boost the Skylab into a higher orbit. But the space shuttle program was delayed, and that particular solar cycle was much more active than they were anticipating, and so the Earth's atmosphere was a lot more heated a lot more at the edge of space, and so it expanded out into space, and that additional air drag on Skylab brought it down, and it famously crashed over Australia. So we do know that space weather does have a role to play in deorbiting satellites, and so it will just limit the lifetime of some of these lower Earth orbiting satellites.
Yeah, well, thank you so much for your question, Ground-Based Space. I know you're a hardcore fan of Space Store, so thank you for supporting us. Thank you to everyone else who has come along to this live show. I hope you guys have enjoyed it. I hope you guys have learned something you didn't know about space weather before. Once again, check out our Twitter, check out our Instagram, check out Stormwatch's Twitter and Instagram as well whilst you're there. Chris, it's been a pleasure having you on the show. It's been amazing speaking to you. Thank you so much for taking the time out. It's been a thunderous talk. I always wanted to say that. All right, guys, we'll wrap up the show there. Thank you for joining us, and we'll see you on Tuesday for the roundup at 7:30. Take care, everyone.
Thanks.
Hi, my name's Nick Howes, space enthusiast, author, writer, broadcaster.
Hi, I'm Terry Mosley, past president of the Irish Astronomical Association, lifelong astronomy and space nerd, absolutely fascinated by everything, both man-made and natural up there.
So every 2 weeks, Terry and I give you the latest, hottest news from space and human spaceflight, robotic spaceflight, and what's happening up in the skies. Please tune in to us every fortnight with the Space Store.